This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let me review, first of all, the idea of initial conditions and why we need both position and velocity. Let's just take the case of one-dimensional motion as an example. And let me begin with a false law of physics. I think I called it last time Aristotle's law. Aristotle thought that in order to keep an object moving, you had to continuously exert a force on it. Of course, we know that's not true. An object moving through free space under its own inertia will keep moving without an external force. But Aristotle's law is a consistent mathematical law. Let me write it down. What it says, I don't know that Aristotle, of course, ever said it this way. I'll say it this way. I would call it my own law, except I know that it's wrong, so there's not much percentage in it. Force is equal, let's put a constant in and call it mass, times velocity. And we can make this a vector equation, or we can simply make it a one-dimensional equation along an axis. It says that without force, you can't have any velocity. If you remove the force, an object will instantly come to rest. A wrong equation. But we can also write this, of course, F equals mass times dx dt. And just to remind you, I often use the notation dot on top of a symbol to indicate derivative with respect to time. So that's Aristotle's law. Now, what do you need? Oh, and we'll also assume something else. We'll assume that the force law is a law which tells you what the force on the object is if you know where it is, where the object is. So let's write f of x. F of x is equal to mass, well, it's fine, mass times dx dt. Now, I say that in order to follow the system, all you need to know is at the initial starting point, all you need to know is the position. You don't need to know the velocity. How do I know that? Well, look at this equation. Supposing you knew that at time t equals 0, this is x, the vertical axis doesn't mean anything right now. Supposing we knew the particle was at x, then we would instantly know the force on it. Why? Because the force is a known function of position. But from that, we would instantly read off the velocity, just from the equation itself. So with Aristotle's equation, if we know x at an instant, we also know the velocity. Now, what about the acceleration? Do we know the acceleration? Let's prove that we can figure out the acceleration. To figure out the acceleration, all we have to do is differentiate this with respect to time. We'll assume the mass, in fact, from here on in, forever and ever, mass is a constant. It doesn't change with time. The mass of an object just stays there. Of course, the mass of an object could change. We could drop the bottom off this and its mass changes, but that's only because we ignored part of the system that fell off. All right, so here we are. F equals m dx dt. Let's differentiate this with respect to time. Then on the right-hand side, we'll of course have the acceleration, mass times the acceleration. What about the left-hand side? The left-hand side will have the time derivative of the force. So let's come over to this blackboard and calculate the time derivative of the force. Why does the force change in the first place? It changes because the particle moves. And depending on where the particle is, the force will change. All right? The force only changes because the particle moves. So let's calculate the time rate of change of the force. That's equal to the derivative of the force. Let's call it the derivative of the force with respect to position. I'm using some crazy mixed notation, partial and The derivative of the force with respect to position, that tells you how much the force changes when you move from one position to another, times how fast you move, dx dt. In fact, if you look at this equation, you'll notice it's correct because you can cancel out the dx. df dt is df by dx, dx by dt. And what it tells you is the force changes with time because it varies with position, and position is varying with respect to time. So this then is df by dx times the velocity. Okay, let's put it in here. df by dt is equal to df by dx times the velocity. Let's forget this for a moment. Well, that immediately now tells us the acceleration. We know the force is a function of position. We can differentiate it and find out how it varies with respect to position. So if we know f of x, we also know df by dx. And the first equation up here tells us what the velocity is if we know the position. If we know the instantaneous position, we know the velocity. If we know the velocity, then we know the acceleration. So, without any further information, using the equation, we can also deduce the acceleration of the object. We can go further. What's the derivative of acceleration called? Jerk. Jerk. The time derivative of acceleration. Let's see if we can work that out just for fun. Supposing we differentiate this equation with respect to time, then we'll have m times the jerk, the derivative of the acceleration with respect to time. Let's just call it jerk, j, which is derivative of acceleration with respect to time. All right, now we have to differentiate the right-hand side. The right-hand side is a product. To differentiate a product, we use the product rule. And that says, first of all, we have df by dx times dv by dt. But that's just the acceleration. That's one term. That's the term coming from differentiating velocity. And then the other term is gotten by differentiating df dx. We're differentiating with respect to time, but that's just the second derivative of f with respect to x squared times the velocity. Forget this for a moment. The time derivative of f of the derivative of f is the second derivative of f with respect to x times the velocity again. It's exactly the same thing as over here, except applied to the derivative of f. Now we have to multiply that by another velocity. Okay. Derivative of f with respect to x times the velocity times another velocity. The upshot is, in fact, we do know the jerk. We, a moment ago, convinced ourselves that if we know the initial position, we also know both the velocity and the acceleration. Well, all that goes in here is velocity and acceleration and knowledge of the force law. So you also know the jerk. I don't know what the term for the derivative of the jerk is. The putz, the schmuck, I don't know. But I don't know what it's called. But you can see the pattern. Differentiate it again, and each time you can deduce the next derivative. That in effect says you can build up the entire motion if all you know is the position at one instant of time. Now, as I said, this is a false law. So let's go to Newton's laws. And ask the same kind of question. So F is now equal to mass times acceleration, which means mass times the second derivative of position with respect to time. Sometimes if I use my dot notation, I'll call that mx double dot. Each dot means a derivative with respect to time. Okay, let's suppose again, I know where the particle is at time t equals 0. That means I know x. That also means I know the force on it, because the force is a function of position. But how on earth am I going to get the velocity from this? I can't get the velocity. What it tells me is the acceleration in terms of the force, And there is nothing in this equation which tells me what the velocity is. Just doesn't tell me. So I've got to add in the velocity as another piece of information, x and velocity, or x and x dot, are what I need to know to get started. Well, if I know x and the velocity, then I can calculate the jerk. Well, first of all, I can calculate the acceleration. The acceleration I calculate from Newton's equation. So now what do I know? I know the position. I know the velocity because I'm assuming that was given to us. And I now deduce the acceleration. From there on, I can continue and compute the jerk in exactly the same way. If I know the acceleration and the velocity, I then compute the jerk, and then all the multiple derivatives. So the lesson is, in Newton's equations, which are second-order equations, which involve second derivatives with respect to time, you need to know, to get started, positions and velocities. You need to know the position and velocity of every particle and every component of the position and velocity. If you know that, then Newton's equations allow you to compute. And of course, you also need to know the force law as a function of those positions. The force law might depend not only on the position of particles, but it might depend on on relative positions and so forth. But if you know all the positions, then it's assumed that you know the force. All the positions of all the particles, then it's assumed that you know the force on every single one of them due to all the others. That's the assumption of Newton's equations. Now, we also talked about conservation of energy. I think I was getting a little bit tired. I tend to do that after 2 hours. So let's just go back quickly and discuss conservation of energy from Newton's equations. Nothing deep at this point. I mean, conservation of energy is clearly a lot deeper than Newton's equations. It follows for electromagnetic radiation. It follows in the theory of electrodynamics. It works in relativity theory. It works in general relativity. It works in quantum mechanics. There's clearly something much deeper about the conservation of energy than just what we're about to demonstrate. But still, we'll start slow. Okay. Now, I gave you the example, a couple of examples where energy conservation fails. For example, if there's friction forces, of course, energy conservation really does work. It works if you were to follow the heat and everything else that's produced by the sliding eraser. But if you ignore all that and just think of friction forces slowing the eraser down, it would seem that the energy, the kinetic energy, the energy of motion, suddenly goes away, and it's not compensated for any change in potential energy. So there are obviously formulas that you can write down which would not conserve energy. All right, I'll give you another example. The other example was the spiral staircase. The spiral staircase, you can think of this way. Supposing you have a force law that always pushes you around a circle in the same direction. The force always points around the circle. Let's not worry for the moment whether centrifugal force takes you off the circle. Let's pretend that there's a good solid barrier, another force, which keeps the particle from moving off the circle. And what's going to happen? If the force is always pushing you around the circle in the same direction, the particle is going to get faster and faster and faster. And it's clear, by the time it comes back to the same position, it will be going faster. There's no possibility of a conservation of potential and kinetic energy. You've come back to exactly the same spot, so therefore the potential energy, if there is any, will be the same, but the kinetic energy has increased, and it'll keep increasing. A force law like this is, again, unphysical. It never occurs in nature. The forces that occur in nature are called conservative, and they are always of the following form. the components of a force, I'm speaking about a single particle now. We'll generalize this to many particles. In fact, we'll generalize it to arbitrary systems. But let's take the case of a single particle. The force, and now think of the force as a vector. I'm drawing it in 2 dimensions. It could be in any number of dimensions, is equal to minus the derivative. I'll write a formula and then I'll explain what it means. This formula, this triangle, is simply a symbol for derivatives, partial derivatives. Imagine that the potential energy is a function of position, and if the position were 2-dimensional, as it is here, it would be a function of x and y. This is the potential energy, U. All right. This formula really just means that each component of the force, the x component of the force and the y component of the force, are equal to minus the derivative, in this case with respect to x, of u of x and y, and minus the derivative with respect to y of u of x and y. That's what the symbol means. It means the collection of derivatives, partial derivatives, with respect to the individual coordinates. Okay. So what it says then is the components of force in a given direction are proportional to how fast the potential energy is changing along that direction. Okay. All right, let's use this to prove the conservation of energy for the motion of a particle. I did it last time, but as I said, I was getting a little bit tired, so I want to do it again and just do it as review. Okay. Let's define the quantity of the total energy as the sum of kinetic energy plus potential energy. Okay, what is kinetic energy? I'll define it for you now. By definition, for a particle moving, it's 1/2 the mass of the particle times the velocity squared. The velocity squared means if there's more than one component of velocity, it means the sums of the squares of the components of the velocity. So in this case with 2 dimensions, it would mean 1/2 m vx squared plus vy squared. More generally, I could write it as 1/2 the mass of the object times the sum over the components of vi squared. Sum meaning vx squared plus vy squared plus vz squared, or whatever the number of directions of space is. Okay, that's the kinetic energy. So that's usually called T. Again, just like P stands for momentum, T stands for kinetic energy. Don't ask me why. And then the other contribution to the energy.
Isn't that also why U is potential?
Yeah, it's also why U is potential. A lot of people use V for potential, but that gets mixed up with voltage, which is potential energy divided by charge. So I use U and I steer clear of V, but other people use V. It also gets confused with velocity. T plus U, that is the total energy. I want to prove that it's conserved as a consequence of Newton's equation, F equals ma. What does that mean that it's conserved? It means that its time derivative is 0. So all we have to do is take its time derivative, use Newton's equations, and prove that everything cancels out when we take the time derivative. That's the exercise, and it's not very hard. Let's do it. Okay, so let's calculate the time derivative of the kinetic energy. Derivative with respect to time of kinetic energy. That is, here it is right here. Here's the kinetic energy, 1/2 mv squared. M is not changing. Mass is fixed. 1/2 is not changing. The thing which might change is the velocity. All right? This, of course, is the sum of squares of velocities. So it's a sum m v sub I times dv sub I by dt. Now what I've done is I've said that the derivative of a square, namely the derivative of v squared is v times the derivative of v. The derivative of the square of something is the something times its own derivative. Whoops, I forgot a factor of, I did it right, but I didn't say it right. The derivative of the square is twice the something times the derivative of the something. All right? That gets rid of the factor of 2. So the time derivative of the kinetic energy is the sum over all the directions of space, the mass times the ith component of the velocity times, now what's dv sub I by dt? That's the component of the acceleration, so we might as well call it the acceleration. A sub I, ith component of acceleration. Let's calculate the time derivative now of the potential energy. And the potential energy is also a function of position. When I write here that it's a function of x, it could be a function of x, y, z, all of the coordinates. What is the derivative of u with respect to time? Well, u varies with time for the same reason that it did before, because the position varies. It varies a little bit if you move in the x direction. It varies a little bit if you move in the y direction. It varies a little bit if you move in the z direction. And so, in fact, the derivative of u with respect to t is a sum of terms, each term being the derivative of u with respect to x times the time derivative of x plus du by dy times the time derivative with respect to y, and so forth. Or I can summarize it by saying it's the derivative of u with respect to the ith coordinate x times the velocity in the ith direction, times the component of the velocity in the ith direction. Again, summed over I. So now let's write down the total time derivative of the energy. It's the sum of these two, derivative of kinetic energy, derivative of potential energy. And we can write down that the time derivative of energy is equal to the summation over all the directions. Let's take v sub I first, and then write ma sub I. That's the first term here. You can see where this is going. I'm grouping m with a sub I for a reason. Okay? And then we have to add to that, again, a sum over I, and it is plus du by dxi, also times vi. Both these terms have the velocities in them. So let's take the velocity outside the parentheses, like so. Well, what do we have? What's ma sub I? It's the force. Mass times acceleration. So this is the component of the force in the ith direction. But what's du by dxi? That's minus the force in the ith direction. This minus sign here. So this is just F minus F. That's what's in the bracket here. Notice that force is minus the derivative of the potential energy, all times v. But F minus F is 0, whether it's multiplied by v or not. So term by term, all you get is 0. Upshot, energy is conserved. And now we're only talking about a single particle moving in a force field. But we could be talking about any number of particles. Instead of thinking of the sum as just the sum over the 3 directions of space, it could also include the sum over different particles. And precisely the same kind of analysis would say that if you have a system of particles, that the system of particles will have a conserved energy, no matter what the force is, as long as the rule is that the force on every particle is minus the derivative of u with respect to its position. Okay. So that was review. I don't remember if we talked about conservation of momentum last time. Did we? No. Okay. So I will now begin reviewing what I did not do last time, but which I had intended to do. And so let's review conservation of momentum. Now, as I said, this was a little bit of trickery and a little bit of magic, and you might say, yeah, but why is energy really conserved? We will come to that, but for the moment, we're just observing that Newton's equations allow you to define a certain thing, namely T plus V, to be called energy. Okay, now let's come to momentum. Now, first of all, let me rewrite Newton's equation in a slightly different form. Nothing very deep. Now, we're talking about a single particle. The single particle has the equation, the force, again, we can do it in components. F sub I is just equal to mass times the derivative of V sub I with respect to T. Again, I simply stands for one of the three coordinates of space. So these are the three coordinates. All right, mass doesn't change with time. So I can bring it into the time derivative and just write that force, I'm not going to bother putting indices down here, is the derivative with respect to time of mass times V. And now give mass times V a name. The name is momentum. Okay? Mass times velocity, and it's a vector. It has components. It has, we can write this for each component. M times V is called momentum. And so another form of Newton's equations is that force is equal to the time derivative of the momentum of an object. Momentum is called P. And so we can make this a vector equation if we like. Force is simply the time derivative of the momentum.
Wasn't that the original formulation of Newton's law, the way he stated it?
I don't know. I don't think Newton actually defined the definition of momentum as far as I know. I'm not sure. It's been quite a number of years since I read the Principia. What assumptions are we making about time? Well, no, we didn't talk about it. We're assuming that there's a universal concept of time at every point in this room. We could have a watch or a clock. Each one of you has a clock. They're synchronized. And we're making the dumbest, simplest Newtonian assumption that time is an absolutely universal thing. At every point of space, we can synchronize our watches so that everybody will agree upon the time, and that time just flows uniformly in the most naive kind of sense. One of the things we have assumed is that the force law here does not explicitly depend on time. We could imagine force laws which change with time. I'm assuming for the moment that that's not the case. All right, now let's come to conservation of momentum. First of all, even if there was just a single particle and there was no force on it, momentum would be conserved because it would say the time derivative of the momentum is equal to 0. So for a single particle with no forces on it, out in outer space, far away in between galaxies, the momentum is conserved, at least to the approximation that we ignore forces on the particle. But that's hardly a very general example. So let's think about a more general example. The basic foundation for the conservation of momentum is another one of Newton's laws about force. Here's what Newton said. He said the forces between objects. Well, first of all, he said the force on every object, and by every object we can mean particles now, everything being made out of particles. The force on every object is the sum of forces due to all the other objects. All right, so if we call this particle 1, then the force on particle 1 is equal to the force on particle 1 due to particle 2, let's call that F12, plus the force on particle 1 due to particle 3. We assume that a particle doesn't exert a force on itself, plus F14, and so forth. Force on particle 1 is the sum, this is 1, 2, 3, 4, 5. Okay. Same thing for particle 2. The force on particle 2 is the force on 2 due to 1. Okay, so notice my notation. My notation is the first entry is the particle that we're talking about. We're talking about the force on the first particle here. The second entry refers to the particle that the force is due to. So this is the force on 1 due to 2. Here's the force on 2 due to 1, plus the force on 2 due to 3, plus the force on 2 due to 4, and so forth. Let's just take I don't want to write too much. Let's just truncate it at 3 particles. And finally, the third particle would have a force on 3 due to 1, plus a force on 3 due to 2. And that's all. Now, Newton's assumption, Newton's law, it's called action and reaction, of course, is that the forces of a particle on another particle, the forces between a pair of particles, are equal and opposite. Right? So the force on 1 due to 2 might be an attraction, for example, is equal and opposite to the force on 2 due to 1. So if 2 is pulling 1 upward to the left, 1 is pulling 2 downward to the right with the same magnitude of force. Now, there was another element to this, that the force is along the line separating the 2 particles, but we're going to not worry about that right now. We'll come back to that. The important point is that the force on 1 due to 2 is minus the force on 2 due to 1. We can make a vector equations out of these if we like. They are vector equations. And what does Newton's law say? It says that F12 is minus F21. F13 is minus F31, and F32 is minus F23. Okay, now let's see if we can explore momentum conservation. What we'd like to prove is that the time derivative of the total momentum of a system is 0 as a consequence of this. What do I mean by the total momentum? I mean the total sum of momentum on all the parts of the system, all the particles that make it up. So let's write them down. Let's do the 3-particle case. dp1 by dt. I'm not going to bother putting vector signs above the think vector. dp1 by dt is equal to f1, which means f12 plus f13, plus all the others if there were more. What about dp2 by dt? That's equal to f21 plus f23. And finally, dp3 by dt is equal to f31 plus f32. Now let's add them up. dp1 by dt, dp2 by dt, and dp3 by dt. That gives us the total time derivative of the total momentum. So the time derivative of the total momentum, dp by dt, is just the sum of everything in the right-hand side. But they cancel in pairs. F12 is minus F21. This is just saying the forces cancel. F13 is minus F31, and F23 is minus F23. They all add up to 0, and it says that the total momentum of any closed system Means a system with no external forces on it. Of course, we might have other forces due to some other object in the system. Then we would have to take it into account also. But if we have a closed system means we've accounted for everything in the system that can exert forces. Then the time rate of change of momentum is 0, and momentum is conserved. Again, it comes from a rather special assumption about Newtonian forces, but it's far more general. It applies to light. If a light ray bangs into the wall, it'll give the wall a little bit of push. It'll change the momentum of the wall. Why? Because the light ray has some momentum. It applies in quantum mechanics. It applies in the general theory of relativity. So it's far, far more general than this little example shows. And our object is will eventually be to write the laws of physics, in particular mechanics, in a form which is so general that we can see why these things had to happen. See? Okay, any questions? Yes? Loud. In Newtonian physics, it is. All right, in classical mechanics, Newtonian physics, and Newtonian physics means forget relativity. In Newtonian, let's put it this way. In Newtonian physics, the speed of light is infinite. You turn on the lights and the room lights up instantaneously. There's no lag. In the real world, of course, forces do not act instantaneously. It takes time for a force when you do something to a particle over here, it takes time for the force to respond over there. That's because of relativity, special relativity. We're assuming Newtonian physics, and Newtonian physics means that forces are instantaneous. So yes, we're assuming they're instantaneous. Again, what's curious is that special relativity undermines that instantaneousness of forces, but it does not undermine the conservation of momentum. So it's somehow much deeper than our examples indicate.
The momentum law seems a little more deeper than the energy law in the sense that
It's easier to derive.
also you can choose any direction, and momentum, the component of momentum will be conserved in that direction. Seems like there are more laws there.
Right, there are more momentum laws than there is energy law. How many momentum laws are there for a single particle, for example? Or how many momentum laws are there altogether for a combined system? 3, 1 for each direction of space. How many energy laws? 1. So altogether there are 4 conservation laws. 3 for the 3 directions of space and 1 for the direction of time. And in the special theory of relativity, they form a complex of 4 related conservation laws, but it's more general than that. Okay, now it's my usual, we're going to need a little bit of mathematics, not heavy-duty mathematics, fairly light, but let's spend a little bit of time. What we're going to do next is we're going to go on to what really is the deep law of classical physics. It's called the principle or the law of least action. And it contains all this junk. The law of least action has all of this stuck into it, plus a lot more. But before we do, we need some math. Elementary mathematics, extremely simple. Math that you know very well. I just want to spell it out and remind some of you who haven't done calculus for a couple of years, so that we're all on the same playing field. The first thing has to do with minimizing functions. This is very elementary. I'm not telling you anything you don't know. If you have a function of several variables, let's start with a function of one variable, function of y. Some known function, not force, it doesn't stand, f does not stand for force now, it just stands for function. F of y. And y is just some generic independent variable. Okay, here it is. Here's the function. It's plotted vertically. I plot f. Horizontally, I plot the independent variable y, and it has some shape, something. The first fact is if you want to find the local minima, now local minima of the function mean the places where if you're there, if you go in either direction, the function increases. A global minimum would mean the absolute minimum, the lowest possible minimum. But we're going to speak about local minima. Local minima mean that if you are confined to that region, you would think that the function was minimum right at that point. What is the mathematical condition for searching for minima? Well, the derivative of a function should be equal to 0, right? That's not sufficient. Yeah. Right. So the first condition, and the easiest one, is that at a minimum, the slope of the function is 0. That says that the derivative of the function is equal to 0 at minima. It's also 0 at maxima, notice. All right. The first condition is that df by dx, or df by dy, total derivative, in this case, total derivative, if it's only a function of one variable, is equal to 0. Now, there are other conditions. The other conditions are basically there to sort out two other cases. The maximum, the f by dy is also 0 at maxima, but you can check whether it's a maximum or a minimum by looking at the second derivative. The second derivative is positive at a minimum and negative at a maximum. But we're not going to worry about that distinction. The principle of, what's the generic term for a function which is either maximum or minimum, and you may not know which? Extremum is one word. Stationary, in fact, there's even another possibility, an inflection point where the function is flat and then goes down like that. Again, 0 derivative at that point. X cubed is a function which has an inflection point like that at the origin. Its derivative is also 0 at the origin. Knowing that the derivative is 0 doesn't sort out these three cases of minimum, maximum, or inflection point. So the word for either minimum or maximum is extremum point. But what's the word for any one of these three? Stationary. The function is stationary at those points. Which means that if you move a little to the left or move it to the right, it neither increases nor decreases. Well, it may increase to second order, but it doesn't increase to first order. The derivative is 0 there. It's said to be stationary. The real principle of least action is really the principle of stationary action. We'll call it the principle of least action and always pretend that we're looking for minima of things. But in fact, it's more general. The principle of action is the principle of stationary action. But I'm not going to draw that distinction after this point now. The condition for a stationary point is that the derivative of f with respect to y is equal to 0. And I'll often say minimum, but I will mean stationary point. Now, supposing we have a function which is a function of several variables, f of x and y. And let's think about it. Let's draw the xy plane. At every point on this plane, the function takes on some value. We could describe the function by a sort of contour map. You've all seen contour maps. You know what they look like. Each contour describing a particular value of the function. And as you move from one contour point to another contour point, the function changes. Well, all right, I don't need the contour map. All we need to do is to remember that the function has some value at every point on this two-dimensional plane. Now, supposing what I want is the minimum, local minimum, with respect to two variables. What that means is a point where the function is minimum no matter what direction you move off in. It could be any number of dimensions. I'm interested in points where the function achieves a minimum, which means that any direction that you move off in, the function increases, however you move.
Think of it as a bowl.
Think of it as the bottom of a bowl. Right.
Are you talking stationary again, or are we just talking?
Yeah, strictly speaking, we're talking stationary, but I'll use the terminology of minimum. And if you want to think about it, think about minimum. You won't be making any serious mistakes, because in fact, almost every case in mechanics, we really are talking about the minimum action.
I have a question.
Yeah.
I think I read that if forces are conservative, that it is not a maximum.
If forces are conservative, it's not a maximum, but I think that's probably not true if there are velocity-dependent forces like magnetic forces, although I've never checked that, so.
That would be the non-conservative case, wouldn't it?
Non-perturbative? I don't know. It's non-conservative. No. Magnetic forces are conservative, but they're different in nature than, let's not get into them at the moment. We'll come back to them. I believe there are cases in physics where the action is not minimum, but they're unusual. So let's just say minimum. Minimum. Let's not worry about that subtlety. All right. Well, first of all, let's suppose we are, here's a minimum right there, and let's look at the function. Whoops, I meant to go right through that point. Let's look at the function as we move to the left or right away from that point. Now the function is only a function of one variable. Think of it as a function of one variable along this line. It should achieve a minimum right at this point. So that means as you move along this line, ignoring all the other lines, the function should be minimum at that point, and that says that the derivative of f with respect to x should be equal to 0. But we can say exactly the same thing about moving on the vertical axis. If the function is minimum at that point, it will be minimum with respect to a vertical motion. So that says the function should have no derivative with respect to y. If you have a function of a whole bunch of variables, let's give them the generic name x sub I now. Function of x sub I. The condition that you're at a local minimum is that the derivative of f with respect to every one of the x sub i's, every single one should be equal to 0. Let's do an example or two just to I think as a function of one variable, we don't need to do an example. Let's take a function of two variables and find its local minimum. Just, in fact, it will be its global minimum. I'm just arbitrarily making up a silly function now. All right, here it is. X squared plus y squared plus 3x plus 2y. Let's put in plus xy plus 7. That's my function. I want to find out where that function is minimum. Right? So I differentiate it with respect to x and set the derivative equal to 0. That gives me one equation. Do the same thing for y. It gives me a second equation. What are those equations for? They're for x and y. They tell me where the minimum is achieved. So I have two equations for two unknowns. Let's work them out, just as an example. The derivative, the partial derivative of f with respect to x, df by dx. All right, that's from this term we just get y. From this term we get plus 2x. This term doesn't depend on x altogether. From this term we just get 3, and there are no other terms which depend on x. So this is the derivative of f with respect to x, pretending that y were just a constant. All right, that's the partial derivative. And our rule is set this equal to 0. That's one equation for x and y. All right, let's do the same thing df by dy. All right, df by dy is x plus 2y plus 2 equals 0. Here are two linear equations for x and y. You can sit down and solve them. Notice that the 7 didn't come into it at all. Why not? Because the 7 is just the height, or overall height of the function, and it doesn't change where the minimum is. All right, so I'll tell you what the answer is. It's x is equal to minus 8/3, and y is equal to minus 1/3. And if that's not correct, it's not important. Is it minus 1/3? I lost the paper that I did it on. But it's not important. There is an answer to the problem, as you can see. It's just two equations for two unknowns. If you have n unknowns, in other words, if you have a function of n variables, then there are n equations like this. N equations for n unknowns typically will have a solution. Not always. Some functions don't have minima. For example, if I took a function that just was like that, forever and ever, it wouldn't have a minimum. There would just be no solution. There would be no point at which the derivative vanished. Sometimes there's more than one solution. For example, if I took a function with a few minima in it. But you have enough equations for enough unknowns to locate solutions. All right, that's mathematical point number 1. You find stationary points or minima by differentiating the function, or another way of saying it is finding points where if you vary the function a little bit, it doesn't change. It doesn't change to first order in the variation, basically. All right, so that's stationary, the principle of stationary functions. Now, we're not going to be interested in minimizing functions of a finite number of variables. We're going to be interested in something which, at the face of it, seems far more complicated. It's minimizing expressions which depend not on some finite set of variables, but which themselves depend on whole functions, whole trajectories, minimizing quantities which depend on a whole trajectory. Before I give you an example, let me just say some words about what the basic problem of mechanics is, and more than that, the basic problem of classical physics, but let's say mechanics. The basic problem of mechanics is to determine the trajectory of a system from its initial starting initial conditions. That's the mathematical problem. Now, of course, in every case, we may not really be interested in determining, if we have 10 to the 23rd particles, determining the trajectory of that system is equivalent to determining the trajectories of all 10 to the 23rd particles. Nobody tries to do that. Instead, we may make some statistical statements about it or some approximate statements. But the very precise question of classical mechanics is determining the trajectory of a system. Now, what does it mean? We spoke last time a little bit about generalized coordinates. Generalized coordinates are simply the coordinates of a system. They could be the Cartesian coordinates of the positions of a system of particles. They could be angles. They could be the orientation of this eraser. They could be any number of different kinds of coordinates that we might use. For example, on the surface of the Earth, we might use latitude and longitude to locate an object. Those are all generalized coordinates, and they may not be Cartesian coordinates. They may be angles or other funny kinds of variables, but they do serve to locate an object in space or locate a system in space. And those are called the generalized coordinates, and they're often labeled by Q. q1 dot 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 through qn. For a single particle, there are 3 q's, x, y, and z. For 2 particles, there are 6 q's, the x, y, and z of one particle and the x, y, and z of the other particle. If there are 10 to the 23rd particles, there are 3 times 10 to the 23rd q's. But as we've seen already, the q's are not enough to be able to predict the future. If you want to predict the future, you also need the velocities. So in a more general abstract language, it also means that you need the q dots, the time derivatives. You need 6 n pieces of information for n particles to predict the future. Now, what does it mean to predict the future? It means to determine the trajectory of the system, which means q1 of t, q2 of t, q3 of t. It means to determine all of the coordinates as a function of time. All of the particle coordinates, or the angles, or the orientation angles, or whatever it is, to determine all of them. Not just one of them as a function of time, but all of them. Such a system of functions as a function of time we can call a generalized trajectory. A generalized trajectory we can imagine horizontally plotting all of the q's. Now, horizontally, I've just drawn 2 dimensions here. 2 dimensions will be a stand-in for any number of dimensions, q1 through qn. And vertically, we plot the time. A trajectory simply means exactly what it says, a trajectory through the space. And a trajectory through the space is a system of q's at every value of time. That's the mathematical problem that's put in front of us by the questions of classical mechanics. To what extent can we determine the trajectory from the starting point? All right, the answer, of course, is given Newton's equations, we can predict the q of t not just from the starting point. We need the q's and the q dots to start with. If we know the q's and the q dots, we can determine the trajectory. The equations of motion, the Newton's equations of motion, what they tell us is every point along this trajectory, they kind of tell us if we're moving in a certain way, how to move next. They tell us that if we know the velocity along here, if we know where we are along here and we know the forces, then we know the acceleration. So that tells us if we know where we are and we know where we're moving, we know where we'll be next and we know where we'll be moving next. The way to say this is that Newton's equations are local equations along the trajectory, and they tell us information, they tell us how to proceed from one point to the next along the trajectory. You don't need to know anything about the rest of the trajectory. If you know where you are over here and you know which way you're going, then you know where you'll be next and you know where you'll be going next. Okay? So they're local equations, and that's why they're differential equations. Differential equations are equations among the positions and the derivatives and so forth, and that's the kind of information that they have in them. Now, of course, if you know this information all along the trajectory, then you can build up the whole trajectory. But the equation itself is an equation which tells you local information. The principle of least action is another formulation of the same physics which looks at the trajectory as a whole. Instead of being given the position and the velocity at a single time, what you're given is different kind of information. You're given the position at the beginning of a trajectory, okay? It could be the position of this eraser at time t equals 0, okay? And after a certain specified amount of time, you're given the position of the system at the end of the trajectory. In other words, you're given the 2 endpoints of the trajectory. So for example, here's an example, here's the eraser. I tell you at time t equals 0, it's over here. I'm not going to tell you how it's moving, so I can't tell you what it's going to do next. But what I will tell you is that after 1 second, it will be over here. There's only one trajectory which goes from here to here in 1 second. There it is. Okay? If I throw it with the wrong velocity, it won't get there. So it's just as good to know 2 points along the trajectory as to know the 2 pieces of information at a single point along the trajectory. Same amount of information. Instead of giving the position and velocity at 1 point, I give you the positions at 2 separate times. That's the problem. That's another formulation of the question of mechanics. Question of mechanics, instead of the initial data problem, the problem of finding a unique trajectory which connects 2 points. Okay. In this form, the principle of nature that governs trajectories is called the principle of least action. And what it says is there's some quantity associated with this trajectory, the whole trajectory, not just little pieces of local information, but the whole trajectory. There's some quantity about that trajectory which is minimum for the true trajectory, and will be larger for every deviation of the trajectory from the true trajectory. True trajectory. Correct trajectory. Here's an example. Take 2 points. For simplicity, we could take them in 2 dimensions. Calculate the distance between them and ask what is the line, well, not the distance, draw a line, draw a curve between them. Draw any curve between them. Calculate the length of that curve, and then ask what curve minimizes the length. What curve gives you the smallest distance along the curve between those 2 points? Now, of course, we all know the answer. It's a straight line. Okay? But what's the mathematics that goes into it? The mathematics that goes into it is minimizing a certain quantity, but that quantity is not a function of a finite number of variables. It's a function of every point along this curve. So it's a much more complicated object than calculating the minimum of a function of a few variables. There's 2 approaches to it. One is the local approach, which I'll show you what it means in a moment, and one is the global approach. Yeah, let's talk about the local and the global approach. The global approach is just what I said. You pick your 2 points, you calculate the distance along the curve. That's some quantity that depends on the entire curve. And then you ask what minimizes the length along that curve. That's something, it's a very global view where you minimize something associated with the entire curve. Now, the local point of view goes as follows. All right, supposing we know, let's focus. Let's take our little microscope here and focus somewhere along the trajectory over here. In fact, for our purposes, let's imagine breaking up the trajectory into a lot of little pieces, each of some small length. Okay? And let's focus right in here. The curve comes in over here, so it's pinned down over here. It goes out over here, and I'm interested in where it goes between them. Let's just suppose in breaking it up into pieces as an approximation. As an approximation, break up the curve into little pieces, and now take 2 of those little pieces and ask where should you locate the midpoint in order that the curve be as short as possible. Now, the answer doesn't depend. Where you put this point does not depend on the rest of the curve if you happen to know this point and that point. If you know the point over here and the point over here, then the rest of the curve doesn't matter. You will have to, in any case, if you want to make the curve as short as possible, and you know that it passes through here and here, then all you have to do is ask, how do you make that little segment between them as short as possible? What's the answer? The answer is obvious. but it's a local version of the same question. It just depends on this little region over here. The answer is obvious. Just go straight ahead. Move this point until this little piece of the curve is as short as possible, right? And go straight ahead. We could express this as a differential equation. We will, as a differential equation, which basically says that the difference in the slope from one point to the next is 0. But it's quite obvious that what it says within this little red region here is just go straight ahead. If you generalize that all along the curve, it will tell you at every point, just go straight ahead. So this is the local version, which says go to each point on the curve and make sure it's just going straight ahead. That's enough to tell you that the shortest distance between here and here is a straight line. Okay. So there are these two different versions of thinking about the principle of least distance. This would be the principle of least distance between these 2 points. Let's see, just for a future reference, let's work out, let's try to define our problem mathematically, even if we won't solve it yet. Let's try to define it mathematically. I've solved it for you. I've told you what the answer is, a straight line. Of course, you knew that anyway. But let's do a little bit of mathematics and state the problem in a mathematical form. Okay, let's take our curve, and I think I'd like to get a better pen. Let's think of our curve as existing in the xy plane. And let's suppose we know that it goes through this point. That's a point at x1 and another point at x2. And let's think of y as a function of x. So there's some curve, and what we know is the value of y at x1, and we know the value of y at x2. In other words, I tell you where the endpoints are, and I ask you to find the shortest curve. Well, the first thing we're going to have to do is calculate the distance along the curve for any curve, and then minimize it. So let's calculate the distance along this curve. We'll call this function y of x. So if you like, this is a problem of minimizing something with respect to a whole function, finding the function which minimizes something. All right, let's calculate the distance along this curve if we know y of x. First, begin with a little segment of size dx along the x-axis. All right, so it's a little gap in the function. It's a little segment in the function going over the interval dx. All right, let's draw it over here. Here it is. It goes over distance dx. Is y of x. Right. And we can also speak of dy. Here's dy. As we go from point x to x plus dx, the function goes from y to y plus dy. Okay. What is the length of the hypotenuse of the triangle? If we add up all these little triangles and add up all the hypotenuse, what's the plural of hypotenuse? I don't know. I guess so. If we add up all the hypotenuses, we'll then compute the entire curve. So let's compute it. Well, this side is dy, this side is dx. The distance along here, we'll call that ds squared. This is square of the distance. S stands for distance. Again, one of these letters that has nothing to do with the word. S stands for distance. The square of the distance along this hypotenuse here is clearly dx squared plus dy squared. Or if I take the square root, it tells me the distance along the hypotenuse. Let me write this in the following way. Let me write ds. I'm going to take it over here. I rewrite it over here. ds is equal to dx, I'm factoring out dx, times the square root of 1 plus dy by dx squared. Where did I get that from? If I bring the dx inside the square root, I have to square it to bring it inside the square root, then the 1 will become dx squared, and this term here will just become dy squared. All right? So I've just factored out a dx. I want to think of x as the independent variable. All right? dy by dx, that's just the derivative of the function y of x. So that's nothing but the function, the derivative of the function. If I gave you a function y, you could differentiate it, and this would be dy by dx. All right, now let's add up all of the little intervals. Adding up all the intervals means doing an integral. So the total length of the curve from point x1 to point x2, let's call it s between 1 and 2, is equal to the integral from x1 to x2 of just this quantity here, square root of 1 plus dy by dx squared dx. Now, I'm not going to do anything with this right now. I just wanted to work out for you in terms of y of x. If somebody gives you the function y of x, this is the way you calculate the total length along here. What is our problem? Our problem is to find that function, y of x, which makes this integral as small as possible. Now remember, when I say that it's as small as possible, what's inside the square root is bigger than 1. It's 1 plus something positive. You might say, okay, look, if I want to make this as small as possible, I will just make what's inside the square root here as small as possible and make dy dx equal to 0. No, that's not the answer to this problem because we're making an assumption. The assumption is that the curve goes between these 2 points. If dy by dx was 0 everywhere, it would just be flat. It wouldn't go between these 2 points. So it's given that the curve goes between these 2 points, we want to find the minimum value of this integral. The minimum value of this integral, and that means the curve, y of x, which does that for us, or the function, y of x. In this case, if we thought of x as kind of like time, and y as the coordinate of a system, this might be determining a trajectory by some funny principle of least distance in space and time. But for the moment, just all this is how to find the shortest distance between 2 points. Now, I haven't told you how to do it. We'll get to actually how you do it, but that's the mathematical problem. Find the function which minimizes this expression. This s here depends on y of x. You can sort of think of it as a function of a function. Given y of x, here's a rule for calculating a number from it. It's a function of a function. It's not a function of a few variables. It's a function of an entire other function. It's a number which depends on an entire function. There's a name for a number which depends on an entire function. It's called a functional. A functional is a function of a function. The result is a number, but the input is a whole function. So the distance between 2 points is a functional of y of x, and our problem is to find the minimum value of that functional, subject to some constraints that it passes through, that it passes through 2 points. Let me give you another example, a couple of other examples in physics where you might want to minimize a functional with respect to a function. A principle of optics is the principle of least time. A light ray goes from one point to another point, right, along a path that minimizes the amount of time that it takes for the light ray to go from that point to another. That's Fermat's principle. How we figured it out, I don't know. But it is a correct principle. Now, you say that just means the light goes in a straight line. If it minimizes the time that it goes from one place to another, and light goes with the speed of light, that must mean it minimizes the distance between the 2 points. Yes, that would be correct if the speed of light was everywhere constant. But we're actually interested in a more general and more interesting kind of setup where you might have a material of some sort with an index of refraction, which means the speed of light, which changes from point to point in the material. All right? Then it's not so clear what trajectory to take in order to minimize the time that it takes. So let me give you an example. Let's suppose we have a material, two-dimensional material, there it is, and the speed of light varies. For simplicity, there's nothing special about this, but for simplicity, let's suppose the speed of light just varies with the vertical axis here. So we can divide this up into little thin ribbons, and in each ribbon the speed of light is different. For example, the speed of light might vary from some minimum to some large value up at the top. Light goes slow down here, and incidentally it goes the same velocity no matter what direction it's going in. That's an assumption. There are materials where light moves with different velocity in different directions, but I'm not doing that. All right, so if the light is going this way, it moves with a certain velocity. If it's going this way, it moves with the same velocity, but the velocity does vary from strip to strip. Okay. Now I want to know what's the path so that the time between this point and that point is minimum. That's the true trajectory of the light ray. Well, if you take a straight line, then that's not as efficient. There may be a path which takes less time. For example, if I curve the path up a little bit, I didn't mean to curve it quite that much, but let's curve it up that much anyway, then it's going to spend more of its path moving where the speed is faster. So it'll want to get to regions, light doesn't want to do anything, but in order to minimize the time that it takes to go from here to here, it might want to get to a region quickly where the velocity is larger and then make most of the path with a larger velocity. So it's not obvious that it goes in a straight line, and it doesn't go in a straight line. In fact, it would go in a trajectory something like that if the velocity of light increased as you moved vertically. You might think, well, maybe the best thing to do is to jump straight up and then straight across. But no, that's not as good because the upward part of the journey doesn't get you anywhere. So it's not as good to just go straight up and go straight across. There's some compromise where you curve the trajectory to get it into regions quickly where the velocity of light is faster, but not straight up and straight across. All right, so what is then the quantity which you're trying to minimize when you speak about the principle of least time? So I'll work it out for you. Just for fun, we'll work it out. Again, we have some solution, which is y of x. And we want to find the y of x, the path, which minimizes the time between two known points. And notice there's a theme here. We're always talking about two known points and asking for the trajectory or the function which interpolates between those 2 points. Okay, let's see if we can calculate the time that it takes to go from one point to another. First of all, again, we'll break up the trajectory into small little intervals. All right? Each interval has a distance which we've already calculated. Here's the distance. All right, so let's write that down again over here. the distance ds is equal to dx times the square root of 1 plus dy by dx, the derivative squared. All right? But on the other hand, what is the speed of light? The speed of light is the distance that it goes divided by the time. So each one of these little segments will take a certain amount of time. All right? The rule is that ds by dt is equal to the velocity, is equal to the speed. Let's call that c. But c is not a constant. It depends on y. I could also take it to depend on x, but just for simplicity, I'm imagining this material, which is a kind of layered material with different speeds at different heights. So c is a function of y. Well, that allows me now to determine how long the light ray spends in each little interval dx. Right? We just solve for dt. So dt is equal to ds divided by c of y. All I've done is solve for dt. Multiply by dt and divide by c of y. Okay? So that's how much time the light ray takes to go from one point to a neighboring point where they're separated by distance ds. But now, here's ds. So we can also write this as dx square root of 1 plus dy by dx squared, all divided by c of y. That's the time in terms of the function y of x. Remember now what we're doing. We have some function y of x, and we want to see how long it takes light to go along that function. dy by dx is just a derivative. If I gave you a function, you could differentiate it. dx, that's just a little x interval from here to here. And c of y is the velocity of light along the curve at height y. What's the total time that it takes to get from here to here? We add up all these little intervals of time. We add them up, which obviously means we do an integral. And so the total time between 1 and 2, let's call it t1, 2, is equal to the integral dx from the starting point, x1, to the end point, x2, start to end, of, here it is, square root of 1 plus dy by dx squared divided by c of y. If I told you what c of y was, and I gave you the function y of x, we could determine how long it takes the light ray to go from here to here. Now that doesn't solve our problem. That just sets up our problem. It tells us for every curve y of x, how long it takes to go from point 1 to 2. Then our problem is to find the curve which minimizes the time. That's obviously harder. All right? Right. So find the curve. Search through all possible curves that you could search through and find out what curve minimizes the time. I'll give you another example. Some other examples where, for one reason or another, you might want to minimize something with respect to an entire function. Well, here's a famous example that everybody who builds bridges knows about. If you have a chain or a cable or a string or whatever, a weighted string or a weighted cable hung between 2 points. Now we're assuming that we know the length of the chain. The length of the chain is fixed. We might ask, what configuration does the chain take? And the answer always is it minimizes the potential energy. I'll just tell you that as a fact now. It minimizes the potential energy. Okay? That means effectively it gets as low as it possibly can because the potential energy is just a function of height. Potential energy increases as you go up. It tries to get as low as it can. Right? Well, it can't drop down through the floor because the chain has a fixed length. This sort of configuration will not be terribly efficient because we can gain some, or we can lower the potential energy in the middle by letting it hang down deeper here. So there's some curve, some function of fixed length which minimizes the potential energy. I'm not going to tell you what the function is. I don't even remember. What is it? It's a catenary, right? Yeah, it's catenary. But if you ask me what a catenary is, I can't remember. Yeah. So that's another example of a problem in which you might want to minimize a certain function which depends on the whole curve. You might want to minimize it with respect to the curve itself.
What is the definition of the potential energy in that case? Is it relative to the...
Oh, it's just the height of each basically the height of each molecule.
I mean, from the fixed points? Or
It doesn't matter because you can take it from the fixed points, yeah. But if you were to change the zero of potential energy, it would just add a constant, and it wouldn't change the answer. But right now, I don't want to set up. I don't want to set up this problem. All I wanted to do is show you some examples where physics requires that you minimize something not with respect to a few variables, but basically with respect to an infinite number of variables, the values of y at every point x. The mathematics is called the calculus of variations. It's the problem of minimizing a functional with respect to a function. All right? The principle of least action is this kind of thing. It is minimizing something that is defined for the whole trajectory now, trajectory of a mechanical system. In other words, a system, where did I write them? Did I write them down here somewhere? Yeah, okay. Not one function, but a whole collection of functions, q1 of t, q2 of t. Remember what the q's are? They're the generalized coordinates of a system, q3 of t. We have a whole collection of functions which define a trajectory of a system. Find the trajectory, which means find the collection of functions, q1 through qn of t, which minimize something. What is it? Minimizing, what is the quantity? The quantity is called the action. That's the principle of least action, that there exists a quantity called an action, which minimizing it with respect to the trajectory is equivalent to the usual rules of mechanics. In particular, equivalent to Newton's laws of mechanics, but is in many, many situations far more efficient and a far better tool than just writing down Newton's equations. So, they're equivalent formulations of the same thing, and which one is easier and more useful depends on the system. But believe me, there are systems where the principle of least action is a lot more efficient than, in particular, if I were to take this eraser, which is composed of 10 to the 30th particles, and I had to write down all 10 to the 30th force laws between all 3 times 10 to the 30th coordinates, it would take me a long time to write down those equations. If I tell you, on the other hand, that the trajectory that this object takes in moving through space and rotating minimizes some action, and that I know how to write down the action, it is a much, much more efficient tool for many purposes.
Intuitively, for me, it seems like the principle of least action might apply Newton's laws,
Yes.
but not necessarily the other direction.
Yeah. That's, yeah. It implies Newton's laws in all cases where Newton's laws would be the underlying description, or one underlying. In any case where Newton's laws apply, it is equivalent to Newton's laws. But it's much more general. It's more general. For example, it applies to problems in special relativity, to the motion of objects in special relativity. It applies to fields. It applies to the electromagnetic field. It applies to basically every classical problem in physics. Not just motion of particles, but motion of waves, fields, the whole works. The principle of least action is the most general formulation of mechanics or of classical physics that we have. So all systems in classical physics that I can think of have a formulation in terms of the principle of least action. Now, if it's not particles, but it's something more complicated, the principle of least action might not, we have to generalize it. But little steps, the little step we're taking now is to think about trajectories for a system of particles.
Have you defined action?
No. No.
I wonder,
Not yet. Yeah.
I remember a test where, an exam where the problem was a frictionless block sliding down a frictionless wedge on a frictionless table, and I remember that most of the students spent 3/4 of their test time trying to write the force equations. This was like an introductory physics class.
Right.
And the people that got that in a reasonable amount of time were the ones who applied conservation of energy and equated it to
Yeah.
conservation of momentum.
Yeah. Yeah. But there are, yes. And of course, that is an example of using more general principles. But there are mechanical systems where you wouldn't get too far with that either, and where the more general principle of least action would be the most efficient way to go about it. All right, so I will tell you right now what the action is. All right. Now, this action is going to seem bizarre. It's going to seem strange. It's going to be a little bit surprising. But the final acid test of whether it's the right action is to test it out for all Newtonian problems and see that the principle of least action gives the same rules as Newton's equations. All right? Once we do that, we will then have a reason to believe that this is the right action. So I'll tell you what it is. It's an integral over the trajectory, so it's now the independent variable is time, not x. The independent variable is time. We have a whole bunch of q's of t, or x's of t, or whatever we like. We calculate the kinetic energy and the potential energy, and we integrate it over time. Integral of the kinetic energy, which is what? 1/2 for an ordinary mechanical system composed of ordinary particles. Let's just think of it for one particle. Well, simplest thing, one particle in one dimension, and then I'll tell you what the generalization is. One particle moving up and down an axis. All right? So the problem then is to find x of t. Find the curve or find the function x of t which minimizes a certain thing, which I will now tell you what it is. It's called the action. You might expect, if I tell you that it has to do with the energies, you might expect that it has to do with the kinetic energy, 1/2 mv squared, which is 1/2 dx dt squared, plus the potential energy, integrated over time, dt. In other words, at every point along the trajectory, you might write down the action for a small interval of time would be the total energy times dt. Now, this is wrong. Bizarrely, the answer is almost this, but not quite. Minus. The kinetic energy minus the potential energy. That's called the action.
Bizarre, that's a good explanation.
In the final analysis, whether you call this plus something or minus something is, of course, a matter of definition. you can redefine a new variable and you can call it w, which is minus u, and put in plus w here if you like. But then, fine, you can do that. Then we have to find out what the solution of the problem of minimizing the trajectory with respect to this thing that you've written down is. What you'll find is Newton's equations, but you'll find Newton's equations, instead of finding the force being minus double dw dx, you'll find it plus dw dx, and you'll find out that the thing that you call w is behaving like the negative of the potential energy. So you can call it anything you want. I will call it minus u of x here, but this is the thing which is called the action. Sometimes action is called I, sometimes it's called S. I don't want to use S because we've already used S for path length, and sometimes it's called A for action. This is the one case where I will use a variable which is linguistically or phonetically or whatever the word is sensible.
Is there an intuitive description then of what the action represents in this formulation?
What I suggest is we go through a bunch of examples. I'm throwing something at you now, and it is not easy to explain where this comes from and why this is the answer. The best thing to do, I think, is to examine it and find out that it is the same as Newton's equations. And then we can go back and say, why did it have to be this to get Newton's equations? I'd rather not try to motivate it at this point and just examine it and see what we get. Okay? So let's hold in suspension our questions about why this is the right thing. But let me notice some things about it. First of all, let's compare it with the principle of least distance or the principle of least time. The principle of least time also had integrals. Now, in those cases, I used x as the independent variable and y as the dependent variable. Now I'm using time as the independent variable and x as the dependent variable. So I pulled a switch on you of notation. The independent variable, which is like x in the previous example, is now t. Instead of trying to calculate y of x, I'm trying to calculate x of t. So the dependent variable is x, the independent variable is t. But let's just compare it with the principle of least distance, for example, or the principle of least time. The principle of least distance told us to compute 1 plus dy by dx squared, integrated dx. If we wanted the principle of least time, the optical principle, we would also throw in here a 1 over c of x, I guess. Y, sorry. All right. First of all, the thing which I'm computing here depends on two things. It depends on y of x, and it depends on dy by dx. Right? So it depends on the function and the derivative of the function with respect to the independent variable. That's also true here. This depends on the function, x of t, and also on the first derivative of the function with respect to the independent variable. So it has the same kind of dependence. It doesn't have a square root in it, but still, the thing in the integrand here depends both on the first derivative of the function and the function itself. Depends on y of x, and it depends on dy by dx. Likewise here, it depends on x of t through the function u and on dx by dt. So it's a similar kind of thing. It's an integral along the independent variable from one time to another. And we will also put in an assumption which is very similar to what we put in the principle of least time. Namely, in the principle of least time, we said that the integral is between two fixed points which we don't vary. We hold the 2 points fixed, and we ask what's the trajectory which takes the least time between these. Likewise, in the principle of least action, we assume that we know what x at the beginning of the trajectory is. Let's call that t0, and x at the end of the trajectory, t1, given, not to be changed. So it's a trajectory between 2 points in space and time. If you like, well, you can see what the analogy is. As I said, the basic idea is instead of giving the position and velocity, you're giving the position at 2 distinct times. Find the trajectory which minimizes this integral of the kinetic energy minus the potential energy. Now, it's very surprising. It's even still surprising to me after 40 years of having studied this, for more than 40 years. And I know the reason why it is. I'm still always surprised that it's the kinetic energy minus the potential energy. All right? So you should also be surprised that it's the kinetic minus the potential, but it is. That's the action. The thing in the integral here, the integrand, is called the Lagrangian. The kinetic energy minus the potential energy is called the Lagrangian. And in a general form, a script L, it's a function of all of the q's. It's a function of the q of t's and the q dots of t's, dt. The action is always an integral over time from the beginning of the trajectory to the end of the trajectory. The integrand depends on the coordinates, x, and the velocities, x dot, or q and q dot. That's the most general version of the principle of least action, namely that there exists something. Here's the law of physics. The law of physics says that for every mechanical system, there exists a quantity called the Lagrangian, out of which you build the action, and then you find the path or the trajectory which minimizes that action. Right? In simple cases, in fact, in all cases that correspond to Newtonian physics of one kind or another, this Lagrangian is always the difference between the kinetic energy and the potential energy. In more general systems, which don't have a Newtonian analog, this Lagrangian may well be something totally different and peculiar, but it will still depend on q and q dot, and the principle of least action will be more fundamental than any kind of Newtonian laws of physics. In particular, this is a Newtonian rule. The motion of a particle in the special theory of relativity is quite different than this, but it still has this form. Okay. So what we're going to have to do next time, we won't do it tonight, is learn how to find, given a Lagrangian and given an action like this, how do we convert the rule of the principle of least action into equations of motion that look like Newtonian equations of motion? How do we go back and forth from a Lagrangian to Newton's equations of motion? And if it's not Newton's equations of motion, what are the equations of motion that follow from a given Lagrangian? Notice that this, if we knew how to do this, if we knew how to solve such problems, we would solve, among other problems, by the same rules, the optical problem of finding the path of least time. So there's a close analogy between optics and classical mechanics. Principle of least action in mechanics, principle of least time in optics, but the methods, the techniques are exactly the same. So the next time we'll work out what are the equations of motion which follow from a particular action principle.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.